talk about improper integrals. Improper integrals, I'm in your notes on page 55. Improper integrals. And the page 55 starts off with this little description about the energy required to launch a rocket to a certain height. And there's this messy formula. It looks something like this. R to R plus H, K over X, physics in action right here. So this is your formula that figured out how much energy to go from the Earth's radius of the Earth all the way out to some height above the Earth. So R would be the radius of the Earth. And we could calculate that. So if you had this constant, and you knew what the rocket constant was, and you knew how high you wanted, we could evaluate that in it. But then the question becomes, well, what if I want to launch that rocket not just to a certain height, but all the way outside the Earth's gravitational field and just goes forever? Is that possible? From what we know, a little bit we know about physics and science, is it possible to launch a rocket and have it not come back? Yeah. So we technically could say, well, how much do I need to get it all the way to go forever? Because once it gets out there without the gravity, it'll just keep going. We couldn't necessarily follow it, but it could, right? So that's the idea. What happens if it goes forever? And that's hard to wrap your brain around. It's not necessarily an infinite amount of energy required to get it to go forever, because once you get it pushed out there, it just keeps going. So we call these types of integrals with an endpoint that's infinity. This is one type of improper integral. The reason it's improper is we don't have numbers there to plug in for our bound. You know, after you integrate, you end up, I'm just changing it up here. You integrate, and then you plug in this number minus when you plug in that number. Well, you can't plug infinity in. It's not a number. So the idea is, well, how do you approach integrals that look like that? Not like that don't look like this, but have an infinity up here. Okay, the idea of an improper integral? So there's two types of improper integrals. This is the first one. So a visual in terms of what it means in terms of a graph. I'm looking at this specific integral here, the integral of just 1 over x squared, starting from 1 to infinity. And I've got the graph on your paper there, you can shade it in. Technically, it goes out here forever, right? You just can't see it, it gets so skinny over there, forever. Just because it's infinitely long doesn't mean that it's a finite, an infinite amount of area. So the question is, how much area is that? Is it infinite or is it not infinite? That's the question. Sometimes it is, sometimes it isn't. And the visual, depending on how accurate you are at graphing, may or may not tell you. If you draw like I do, something that's infinite, something that's finite will look like they're exactly the same shape. So that's why we have to do the integration. Everyone understand the question? Like, well, it seems infinitely long. It is, it goes forever. But if it gets skinny fast enough, that part that's off in like the tail might be so small that it's negligible. That's the question. So here's how we're going to approach it. You know, I could pick a B right here, just find the area from 1 to here. I mean, that's definitely a finite amount. And I could keep moving further and further. And at some point, I can go far enough out that whatever's left over is so small you can't really count it. That's the idea. Or maybe it's not. So what we do is we have to go back to what you learned in Calc 1, way back when you learned the idea of limits. Notation turns out to be crucial here. So what we're going to do is we're going to take this integral from 1 to infinity, and we're going to rewrite it as the integral from 1 to some stopping point b. Because we can find that integral. So for example, if I wanted to stop right here, this b right here, I can find that integral. This red part in here. Could you find that integral? If I put a b there? I would have a b in the answer, but we can do it. Let's do it. Let's do it. It'll be fun. The integral of 1 over x squared? Negative 1 over x, so I'm going to rewrite it and show where that came from. He's rewriting that as x to the negative 2. And so then when you add 1 That's x to the negative 1. So it ends up negative 1 over x, evaluated from 1 to b. You guys okay with that? It's x to the negative 1. Then we plug in the b and we plug in the 1. Negative 1 over b minus negative 1 over 1 plus 1. So if I wanted to say integrate out to 1,000,000, from 1 to 1,000,000, if I want to go from 1 to 1,000,000, this would be negative 1 over 1,000,000 plus 1. Do we agree? Yep. If I want to. And if I want to go out to 1,000,000,000,000, it'd be negative 1 over 1,000,000,000 plus 1. No problem. But what if I want to go to infinity? You can't plug infinity in. Do not write it that way because you can. It's not a number. So here's the one thing that we do different. We write the integral, and then we say, okay, fine, let's take our old stuff we know about limits and let b approach infinity. Let's find this limit, this integral that goes to a stopping point, but then let's push that stopping point further and further out to the right. So the first step whenever you're doing one of these improper integrals is to rewrite it so it actually has finite bounds here, and then you take your limit. And then you have to remember what you learned in Calc 1, which was not just the other day for some of us. I already did the integration. We know it's going to equal this. In the future, I'll do the integration along with it, but we just did that integration. What happens to this as b approaches infinity? What happens to this term right here? It goes to 0. Do you remember that from Calc 1? Any constant divided by something that approaches infinity always goes to 0? If you don't remember it, imagine how big this number is. Pretty tiny little number. I don't know, quadrillionth. I made that up. I didn't count my zeros. That's equal to 0.0000. I'm going to put approximately. So I didn't count my zeros. They should match up. Do you agree that term is so darn small eventually doesn't even count? So what's the answer here? 1. It's just 1. I better be careful. It's equal. It comes from here, not from there. What does that mean? That the integral is 1? In terms of my picture.
Is the area is 1?
Yeah, the area underneath this curve, starting here and going out forever, is 1. Imagine if we were measuring in feet. This would be 1 square foot worth of area. Like if I had to go buy some paint, I'm like, I need enough paint to cover 1 square foot. Yes.
What if you would have a variable divided by constant?
If it had been x over 1 this way, something like this?
Right.
You're talking about the limit question,
Yeah.
I'm assuming? So now the numerator's getting infinitely large.
So it just goes to infinity?
So it goes to infinity. Because you have an infinitely large divided by 3, it still really keeps getting bigger every time x gets bigger. Yeah, so the variable in your numerator going towards infinity always will go off towards infinity. But in your denominator, if it's under a constant, will always go to 0. So 1 square foot worth of paint. So I could go, yes sir?
So you have a finite area for unlimited.
For an infinite curve. Isn't that mind-blowing? I love it. Imagine if I asked you to draw this curve forever. Number one, we'd run out of time and we couldn't do it. And I would run out of ink. There are not enough pens in the world for me to keep drawing this forever. I just can't, there's not enough. I can't keep making them fast enough because I have to keep going forever. But I can go to Home Depot right now and buy enough paint to paint that. I only need enough to cover 1 square foot. That's what's mind-blowing. It's infinitely long, but the area is finite. Isn't it weird? Very weird. We'll see a few of those this semester. And it's not always true. Some have an infinite area, some have a finite area, which is why we have to take the limit each time to figure that out. Other comments or questions? I like the weirdness of it. Okay. So let's look on the next page. There's some definitions. They look all complicated, but really it's just telling you to replace your infinities with constants. So it says that if you have an integral from a to infinity, like the problem we just had, right? We started at a constant and we went to infinity. So if it's one of those, then we're going to rewrite that from a to b, and then let b approach infinity. That's just a generic statement for what we just did with that problem. If there's an infinity here, replace it with a b and then let b approach infinity. The next one is, oh, well, what if you start down here at negative infinity and you go to some constant up here? So now the left-hand endpoint goes out there over to the left. The only thing that's going to change is we're going to rewrite that as an a. And then take that limit afterwards. Same idea. And then the last one says what to do if it's negative infinity to infinity. What if both of them are infinities? Yeah, we'll just do a and b. And what we have to do actually is introduce a c of some sort. Let me talk about a picture of what that would look like. So say I want this curve here. Anyone who's had statistics recognize the normal curve goes out there forever. It actually has a finite area. Its area is also 1. But if I wanted to write the limit, it would look something like this. The left side's going out to negative infinity, the right side's going out to positive infinity. So what you have to do in that case is just pick any point you want in the middle and stop there and break it up into 2. It doesn't have to be directly in the middle even. I'll use the same notation as above. Did we use C? Okay, good. So say I just choose a C right here. I want to talk about finding this area and adding it to this area. So the first thing I would do is talk about going from negative infinity to C. That's the polka dotted area. Plus, from C to infinity to get the striped area. See what I'm doing there? And then for each of these, you'd have to write them each as a limit and take those. So the generic shortcut is change all your bounds to constants and then take limits to get to those bounds. If there is no bounds at all, just pick anywhere in the middle. I can stop at 5 if I want. I can stop at 48, as long as I go somewhere and I continue from there. Questions on that notation? Okay. Before we do the next example, there's some important words that are going to come up now and all over chapter 11 when we get there. We talk about whether or not that limit exists. So in this case, the limit was 1. There was an answer, we got a finite answer. So it says if the limit exists, we say the integral is said to converge. So we say this integral converges. It converges because it had an actual finite answer. It converged to a limit. If it still gets infinitely large and blows up and goes off to infinity, then we say that it diverges. So when you look at the directions for these problems, it'll be evaluate these integrals and indicate it for if it's divergent. So if the answer might just be, because the answer turns out to be infinity, we'd say it diverges. Otherwise you get an actual answer. Those will come up quite a bit. Okay, let's look at example 1. I'll give it this one. So this integral converges. example 1 looks like the integral from 0 to infinity of e to the negative 3x dx. We want to evaluate this integral or say that it diverges if it doesn't have a constant or a finite answer.
I think you're missing an x up in the next.
Oh, I am, thank you. It'd be a lot easier without the x. Sorry about that, did you guys see that? There's an x up here? Much easier, it would have diverged for sure, it was that. So as soon as I see that it's infinity up there, that tells me it's an improper integral, what do I need to do?
You're gonna change it to a constant.
Yeah, change this to a constant and write the limit in front of it. So I'm gonna do that all at once. I'm going to change it to a b and let b approach infinity. You don't have to use b, some books will use t, some books will use u, just as long as you pick a variable and stick to it. So the infinity got changed to a constant, and that constant now has to approach infinity. Essentially what we're going to do now is just focus on this part and just carry this along until I'm ready to use it. So I'm going to take the limit eventually, and yes, you need to rewrite it because they're not equivalent without the limit sign there. What's the integral of e to the negative 3x? Oh, you're close. Did you say negative 3 to the negative 3x?
Negative 1/3.
Negative 1/3. I think you said negative 3, huh? Everyone okay why it's negative 1/3?
Yeah.
Because you're dividing by that derivative of the negative 3x? Those are the ones that I call the mental u substitution or the reverse chain rule. Now this constant right here, this negative 1/3, is not going to be affected by this limit. I like to actually pull that all the way out front. All the way out here just to get it out of my way. So I'm going to do that. And then I'm going to evaluate this. And I get e to the negative 3b minus e to the 0. See what I'm doing there? Plugging my b in, plugging my 0 in. Now what should I do? Yeah, I can take the limit now. Some people can take the limit now. Other people can't see what happens with the negative exponent is clearly. Some of you can, and I'm fine with that. So if you don't recognize it, I recommend rewriting your negative exponent so it looks like this. And I'm going to simplify my e to the 0. But you're right, we could have done it there, Jose. I just rewrote the e to the negative 3b. It helps to write it as a fraction because now when we take this limit, what happens with this term? If the denominator goes to infinity, like that last one we did, so this term right here actually goes to 0. 1 over something infinitely large. So we end up with 0 minus 1. Once I've evaluated that limit, I don't need to write it again. The answer is 1/3. So this integral converges. Most of the time, you won't be asked to say that it converges. You'll be asked to either evaluate it or say that it diverges if it doesn't have an answer. But this means it converges because we got a number here. You good? Not too hard? All right, what's next? Look at example 2. Doesn't look much different. Has a picture next to it, which I'm going to talk about after we evaluate example 2. I want you to try example 2, actually. You try it. You try example 2. We'll see what happens, and then we'll talk about it together. I'll write it up here for you. Example 2 wants you to evaluate from 1 to infinity 1 over x dx. Try that. See what happens. While you do that, I'm going to draw this picture that's coming up. A lot of you were close, if not all the way there. First thing we're going to do is rewrite it. The integral from 1 to b of 1 over x dx. And then, excuse me, we're going to recognize that the integral of 1 over x. What's the integral of 1 over x?
Natural log.
Natural log of absolute value of x. Technically it's absolute value. I don't need to write it here though because my values here are already positive. So you don't have to put it, it's not wrong. Evaluated from 1 to b. So this is then the limit as b approaches infinity of the natural log of b minus the natural log of 1. And here's where you need to know the natural log function. It needs to be your friend. Helps if you know what it looks like. Everybody know what a rough sketch of the natural log graph looks like? Well, I like your hand signals back there. Doesn't give me hand signals back there. It looks something like this.
Wait, but I have a question, isn't it the absolute value?
Say that again?
And because the absolute value, wouldn't it diverge?
We're not done yet. It might diverge. We're not done yet. I'm just graphing this function. The reason I'm graphing that function is I want to look at it and ask myself what happens to that function as I move further and further to the right. Right? B goes to infinity. What happens as I go out towards infinity here? It's going to infinity, really slowly, mind you, but it's going up forever. So this part right here is approaching infinity in the long run, which means that this term right here is approaching infinity. What's the natural log of 1?
0.
0. So this goes to infinity minus 0, which is infinity. So what can you tell me about this integral? It diverges. It diverges. Or it is a divergent integral. Yes?
So would you want us to box up the infinity and divergent, or just the divergent?
Just the divergence. So technically the answer is always either going to be what the actual value of your integral is, after you take the limit, or it's going to be the word diverges. Now obviously you're going to show me why it diverges.
Yeah.
But we don't say infinity is the answer. We say it diverges. It's a divergent integral. What were you asking about absolute values?
I'll say, because the absolute value is divergent, because even though x is negative, it's still going to go y in the positive direction. So as x gets further towards the negative side, or as x approaches negative infinity, y will still be approaching infinity.
That would be different, but because our x's are going from 1 to positive infinity, that's why we don't even care about the absolute values in this case. We're just looking from here over. And as you go that way, those y's just keep getting higher and higher.
So on the exam, it doesn't matter if you have the absolute value, just as long as like your
No, I think I know what you're saying. So you want to know because I didn't put the absolute values here?
yeah, so like it doesn't. Well, basically, I'm saying like you wouldn't mark this wrong if we have this as long as like our bounds are both positive.
Correct. So in this case, because our bounds are positive, I know I don't need to put absolute values here because it's already positive. If I didn't have bounds here, or if these had negatives in them, then I would definitely need to put some absolute values there.
But if you put it in there either way, it doesn't
Yeah, it's not wrong to always include it, but I get lazy. I'm like, oh, I don't need them, and I leave them off sometimes. But I only leave them off if it's accurate. Okay, so the picture off to the right of this example turns out to be really important. I tried to recreate it, but I'm clearly not a very good artist. But my lines are not as smooth as they are in your graph. But basically what I graphed is 3 functions that almost all look the same. Some are just steeper or flatter than others. And in general, we're calling of the function 1 over x to the p, where p could be any number. So for example, if it was 1 over x squared, we did that one, I don't know if I saw here anymore. The very first one we did 1 over x squared, and that one that one converged. Right, that one converged. So this black one right here, that's the one that had the finite area even though it was infinitely long. So the black one converged. What about the green one? The green one is 1 over x, which is 1 over x to the 1. I'm changing colors, so be careful. What happened to that one? 1 over x to the 1. It diverged. And the black one was 1 over x squared, and it converged. So the area underneath this guy is finite, but the area underneath the green one is infinite. That's what we just found right here. It's just, and on the picture it's even better. So this area here, it's not even double, it looks double, but even if it was double, you think 2 times the finite number. But what happens is it gets flat so much slower. It takes so long to get narrowed down here that it just keeps adding more and more and more area forever, and it doesn't ever get to a finite answer. But visually, the graphs don't look much different. That's what I was talking about earlier, especially if you draw like me. You can't tell by looking. So if this one diverged, this one converged, what do you think that red one's going to do?
Converge.
Converge? Is this more area or less area than the green one? It's more, right? Because the green one is everything here. Underneath the red's even more than that. More than infinity. Never mind what she says. You guys see that because the red one is higher, the area underneath this red one is even more than this one? So if this one diverged, and this one converged, what do you think is going to be true here now? Just going to change your mind. 1 over x to the 1/2. It better diverge also, right? Because it's even more area. So what we do, these functions come up so often, we call them p functions, later on they'll be p series, powers of x, that we can pretty much say when p is in this category, it's going to converge, when it's in this category, it's going to diverge. What do you think the answer is? It's going to converge if what? It converges sometimes, and it diverges sometimes. What is the sometimes? That's the question. If p is what?
It converges if p equals 2.
So if p equals 2, it converges.
Would it diverge
Say that again?
if it was greater than 2?
We should maybe check that.
Oh, that's
Diverges
posing the
when it's
question.
less.
Oh yeah, it's a question. Where did we see that it diverged?
On
Second part.
At 1 and at 1/2.
So when it's less than 2.
Say that again?
Less than 2.
Less than 2? So here's the problem. We didn't check anything between 1 and 2.
Oh.
We know it diverges at 1. Let's go with it. We know that if it's less than or equal to 1, we agree it diverges. Because the green one we know diverges, anything higher than that, right? It'll keep it up. That diverges. If it's 2, it converges. Oops, I wrote diverges twice. But what about in between there? What if it's 1.5? We need to find out. How are we going to find that out? What if it's 1.01? Heck with 1.5. Let's make it closer to 1. Just a little bit. What if it's 1 over x to the 1.01? Barely more than. So we're talking about what's happening between 1 and 2. Everyone see what we're trying to figure out here? what happens in between 1 and 2? Because this one converges, one diverges, there's gotta be a cutoff somewhere. Let's just work on this integral here by itself for the moment. Taking off the bounds just to investigate. If this is x to the negative 1.01, what's the integral of that? We can do it. Decimals won't kill us, I swear. What do we do to integrate this? Add 1 to this, right? If we add 1, we get x to the negative 0.01 divided by negative 0.01. Well, that's a constant that we don't care about. I'm running myself into the corner here. Times. Can you see that, Nick? What's going to happen if I let that approach infinity? If I put a b in there, and a b approaches infinity, what's going to happen here? The denominator is going to be approaching infinity. So it's going to go to 0, which means what? It will converge. If I get that x in the denominator, that's what makes it converge. So it converges to p equals 2. It even converges if it was 1.01. We just checked that one. What do you think the general rule is? P is greater than 1. It converges as soon as p is greater than 1. I don't care how much greater than 1. It could be 1.00000000001 more than it, it will still converge. Because it will always give you a little left to put in that denominator. It's that darn ln x that made it diverge. So these are going to come up again and again when we get to chapter 11. I'm going to go, remember back in chapter 7 we talked about these p integrals? So some of them you can just look at them and tell me whether or not they're going to converge or diverge. So if I give you a problem here and I ask you to integrate this 1 over the square root of x dx, some of you will do no work and you will just write down a couple pieces of information and I'll be fine with that. Is that one of these?
So 1/2.
Yeah, it's a p of 1/2, right? P equals 1/2. It diverges. That's enough information for me right there. You're recognizing it's in that form. You're recognizing it's a 1/2. Questions? Save yourself some work by looking for those patterns. Okay, let's look at example 3. We'll take a break. We'll look at some other types after that. Example 3. It's not one of those 1 over x squareds anymore, of course. Right after we figure those out. Example 3, we want to evaluate 0 to infinity of 1 over 1 plus x squared dx. This is a nice little review problem for our exam coming up. Do you think it converges or diverges by looking at it? Does your gut tell you anything? You think it converges? Why?
Because it's x squared.
Yeah, he sees that x squared. If it was just like this, we would know it converged. We just talked about that. So it's pretty close to that. So it looks like it converges. Turns out you're right, it does. But we're going to find out exactly what it converges to. So, what should I do first?
Replace infinity with b.
I couldn't hear you again.
Replace the infinity with b.
Replace the infinity with b and take a limit.
Yeah.
So from 0 to b, and take the limit as b approaches infinity. So before anybody says anything, on the exam in a week and a half, it would be really helpful if you recognized this function that you're looking at and knew the antiderivative of it. Some people know it. This has come up numerous times and I've said, oh, watch it, it's going to keep going up all semester long. Inverse tangent. That's the derivative of inverse tan. This is the derivative of inverse tan. So when we integrate it, it's not one I'm going to give you on the test. If you don't recognize it, the only way to figure it out is to do a whole trig substitution, which you could do for fun. I think it'd be fun. But it's better to recognize it. The inverse tan of x evaluated from 0 to b. Keeps coming up, that inverse tan, all semester long. So that's the inverse tan of b minus the inverse tan of 0. Now we need our trig memory. I'm going to start over here because the 0 is more concrete. This means, tell me the angle whose tangent equals 0. What angle has a tangent of 0?
0?
0. That one's good. There's a question mark on the end of this statement, but at least he answered. This one says what angle has a tangent of b? Well, we don't know what b is, but b is approaching infinity. So what angle has a tangent that's approaching infinity or a tangent that's undefined? I'm going to draw you a little rough sketch of the inverse tan function, or excuse me, of the tangent function. It looks something like this, and then it has a little asymptote, and then it does this again. I am not an artist, as you can see. Have you seen this before, when you learned trig from somebody else?
Yeah.
Maybe you learned it from me, I don't know. What angle has a tangent that's approaching infinity? Where is that on my picture? Where are these? This is the tangent values. These points, where are they approaching infinity? So you're right, Nick, it's pi. But right here, these values are heading up there towards infinity. That's where the y's are going up towards infinity up here. You see that? And if you remember this function over here at pi, oh, pi over 2. Sorry, Nick, you were wrong.
I said pi over 2 wrong.
Oh, did you? Sorry, I thought you said pi, and then I agreed with you and then corrected it. He was right all along. Pi over 2. Okay. I thought about that. Wait, that's not pi. Do you all agree that as the x's get closer to pi over 2, the tangents are approaching infinity? So if the tangents are approaching infinity, what's the inverse tan approaching? Pi over 2. That's the answer to this integral. It's pi over 2. That's a weird one. Gotta know where your tangent's undefined. When you're dealing with the inverse trig functions, instead of thinking of it approaching infinity, it's easier for me to think, where is it undefined? And the tangent's undefined when your denominator is 0. Questions on that one? So that's a convergent one also. Okay, let's take a break. Take a 10-minute break from here. We'll come back and then we'll talk about a different type of improper integral. Yay! Because this will not yay? It'll be fun. Okay, let's keep going with our improper integrals. I'm going to save example 4 for the end of the class if we have time, because it's actually more of what we've just been doing. I want to make sure we have time to talk about the other type. So everything that we were doing up till now we call type 1. Those are obviously improper integrals because you can see the infinity right there, and that's what makes them improper. Type 2 is not so obvious. I'm actually going to, before I talk to you about the definition of it, I want to show you an example of one. On page 59, I don't know why my example started over again. Example 1 for type 2 looks like this. The biggest mistake people make on an exam is they don't recognize when they have an improper integral. And this is an example where it's not so recognizable. You don't see the infinity on there, so what's the problem?
1 minus 1 will be undefined.
Aha, the function is undefined at this endpoint right here. If I plug 1 in there, the function's undefined. That means there's an asymptote there. So a visual of what this looks like is what's on the previous page, on page 58, not necessarily this exact one. But it looks something like this, where you have an asymptote here, and then your graph maybe does something, and you stop over here at B. So the problem is now, not that this is going out to infinity, but this is going up to infinity up here. And the question is, you know, what happens up here? How does it get cut off? Does it keep going up and get skinnier? What's going on up in there? So this part's kind of getting infinitely tall as opposed to infinitely to the right. We're going infinitely high now because it's approaching this asymptote up here, which I can't draw very well. And the only way to recognize that is to inspect your original function compared to your bounds here. Yeah, it's defined at 2. I can find out what that function looks like. But at 1, it's undefined, which means in this particular example, there's an asymptote here at 1. You change this to a 1 in this case, and to 2. What happens at 1? It's coming infinitely from the top now. But the approach is the same, it's just recognizing that you have one is the issue. So in this case, we would change it from A to B, A to 2. By the way, I like to write my dx over here to the right, so then I don't get lost. Looks prettier to me over there. And then guess what I'm going to put here? The limit as A approaches 1, but more specifically, bless you, from the right. Remember that from algebra? The little tiny plus sign there? Because in this interval, I'm only heading this way. I'm not coming on the other side of that asymptote at all. I'm only coming towards 1 this way, from the right. It matters because from the right and from the left sometimes give you a positive or a negative. The other part would be down here somewhere, and that would be something else. We don't want any of that. That's not part of our interval. Okay, with what a type 2 looks like? Not obvious, but by inspection it tells you. Okay, so let's keep going. Recopy my limit sign. A approaches 1 from the right. It's the integral of 1 over 1 minus x. Is that a natural log of 1 minus x? There's more. I hear you, everybody's talking real quietly. Someone want to speak up louder, tell me what you're saying? There's something missing here. There's a negative sign in the front. Why?
Because you have the derivative of the
It's
inside.
derivative of the inside, right? Derivative of the inside is a negative 1. Be careful with those. Negative sign out front, evaluated from A to 2. Like the integration's not hard enough, now I can keep track of everything. So this will be limit as A approaches 1 from the right of negative ln of 1 minus 2. Oops. Value sign there. natural log of 1 minus a. You guys okay with my plus there? Minus the negative? So I need to take the limit as a approaches 1 from the right of negative natural log of 1 plus the natural log of 1 minus a. What's the natural log of 1? 0. Now, let's figure out what's going on here. A is approaching 1 from the right, which means that this expression inside the absolute values is approaching what? Just this part. Someone just said it. This part is approaching, if A is approaching 1, this part's approaching 0. What happens to a natural log? I erased my picture, put it back over here. Here it is, it's almost still here. What happens to the natural log as you approach 0? Negative infinity. See that? As I get closer to 0, my y's are going towards negative infinity. So because this inside part's approaching 0, natural log of 0 is undefined, but it's approaching negative infinity, so this part goes to negative infinity. So the answer is negative infinity. Which means what? What'd you say, Maya? It diverges. What does it mean when an integral has an answer of negative infinity? What the heck does that mean in terms of a graph? It's going down. The graph must be below the x-axis and forever infinitely large below the axis. If we drew a rough sketch of that, over here at 1, and here's 2. The graph looks something like this, roughly like this. So what we're saying is that from 1 to 2, this area in here, it's negative because it's below the x-axis, and it doesn't get skinny fast enough. It just kind of keeps adding more and more and more area forever the closer you get to that asymptote. That's why the answer is negative infinity, because the area is below that x-axis. So that's a type 2. And it could be on either side. Type 2 could have an asymptote on the left. It could have an asymptote on the right. Or it could be like that other one, it could have an asymptote in the middle. Those are the trickiest ones to recognize. Chad was just asking me about one of those before the break. One in the middle would look something like this. And I want to know the area from A to B. And it has some asymptote here. But it keeps going up there forever, right? There'll be another one where this is the hardest one to recognize because it's undefined somewhere in your interval. If you don't recognize one of these, you'll get an answer when it diverges. Happens all the time. Let's look at an example of one of those. I'm going to skip ahead again just because I'm worried we're going to run out of time. I think we're good. I'm going to flip over on the back. Where's one of those? Do I not have one of those? Oh, it's example 2. There we go. It's example 2. It is there. Look at example 2. If you had seen example 2 before today, you probably would have said, oh, I can do that. Right? If I'd given you that in Calc 1, I can evaluate that. We do a little U sum. There's nothing disturbing about that, just looking at it. But what makes it an improper integral? What makes this an improper integral?
plug in a 2, you'll be able to find.
Yeah, it's undefined at 2. This function is undefined at 2. And 2 is in my interval here, between 1 and 4. There's an asymptote right in the middle there, probably just like this. So right here at 2, it might go up towards infinity. We don't know if it goes to infinity or not. We have to check. There's at least one on the lab that you can calculate and just plug in the endpoints. It happens all the time, and it does not give you the right answer. Yes?
Does the p being less than 1 have anything to do with that either?
That p being less than 1, that only applies when we're talking about heading out towards infinity,
Okay.
because we're talking about how steep it gets out here to the right. Everything changes when you're talking about going vertically. I'm glad you noticed that though. So he was talking about this 2/3. If it was heading off towards infinity, that would definitely tell us what was happening. But because it's not infinity, we don't know. It might converge, it might diverge. Everyone clear that 2 is the issue? Okay, so we're going to break it up then at 2. We're going to say, fine then, do the integral from 1 to 2. Plus the integral from 2 to 4. What that essentially is doing is looking at, say, this piece on the left, separate from the one on the right. Each piece by themselves has to converge. I have to have a finite amount on the left plus a finite amount on the right. Now, we want to make sure we write it out carefully and accurately. What do I have to do here?
There's like 3, 2, and
The 2 has to be replaced with a b because it's undefined at 2. So I'm going to take the limit as b approaches 2. I'll talk about from the right and left here in a minute. Am I approaching 2 from the left or the right? From the left, he says? I'm going from 1 to 2. From the left, right? From 1 over to 2. I'm only going to be on the left of 2. Sometimes people need to draw a number line. Here's one to visualize it. If I'm in this region, I'm only on the left of 2. So I'm approaching 2 from the left. Plus, for this guy, I'm now going to make it, oops, A, not B, sorry. It doesn't matter if you use A all the time or B all the time. I like to do A for the bottom and B for the top. It doesn't really matter though. Is this one left or right? From the right, same reason, right? If you're starting at 2 going to 4, you're on the right of 2. You see that line? Two separate integrals. I'll warn you, I don't know how many times I'll warn you. There'll be one like this on the exam that diverges. But if you integrate it and plug in the 4 and the 1, you'll get an answer. I'm just saying, if you don't recognize it was undefined in the middle, it's going to give you an answer that's wrong. And technically it's infinitely high if you ignore that. Okay, what should I do now? What'd you say, Joseph?
it could be something.
Yeah, we can start integrating now. I would probably rewrite them as negative exponents, makes it a little bit easier to integrate. I think I'll do that next. B approaches 2 from the left, 1 to B. This is x minus 2 to the negative 2/3. It's easier to integrate that way. 2 from the right, A to 4. I'm just rewriting those as negative exponents so that the integration is easier for me. What's the integral then? That. positive 1/3? And then I have to divide by that 1/3. So it's 3 times x minus 2 to the 1/3. Agreed? Evaluated from 1 to b. And luckily over here, the integration is exactly the same. Oops. 2 from the right of 3 times x minus 2 to the 1/3, evaluated from a to 4. That's an a right here. I changed my a into a b. Are you guys catch that? This one, the second one was an A. I rewrote it here as a B accidentally, and I fixed it. Now we need to plug everything in. We got this. The limit as B approaches 2 from the left of 3 times b minus 2 to the 1/3 minus 3 times 1 minus 2 to the 1/3. That's just the first one. Plus the limit as a approaches 2 from the right of 3 times 4 minus 2 to the 1/3 minus 3 times a minus 2 to the 1/3. Lots of details here. The process itself isn't really challenging, it's keeping track of the details and making sure you're doing your limits properly, they're the harder part. Questions up to that? Most of you seem to be done scribbling, copying, catching up with me. So what happens? If b is approaching 2, what happens to this term right here? It just goes to 0. It's not a problem anymore because this isn't a negative exponent anymore. This is just 0 to the 1/3, the cube root of 0, that's just 0. It was a problem over here because it was undefined, division by 0. But now we can just evaluate it at 0, and that's just 0. So this guy is negative 3 times the cube root of negative 1, so that's just 3. First one's 3. 1/3 just means a cube root, right? Okay. What happens over here when a approaches 2? It's 0 again. And then this is just messy. This is 3 times 2 to the 1/3. So it's 3 times the cube root of 2. That's your answer. And that means that this integral actually converged, which is exactly the opposite of what Zach was thinking when he saw the 2/3. Is, can we use the p property? It should have diverged if it was a p, but since it wasn't approaching infinity, it actually ended up converging. Yes?
I don't understand why for p minus 2 goes to 0.
Because this will just be 2 minus 2 inside here,
Oh, okay.
and 0 to the 1/3, the cube root of 0 is 0. So when you can just plug it in and you get 0, then you're fine. The problem was over here, 2 minus 2 was 0 in the denominator, so it was undefined over here. But over here, the 1/3 is not in the denominator anymore, so that's just equal to 0. Does that help?
Yeah.
Just cube root of 0. Other questions? Now, let me show you something real quick. A warning. This is what one of you, hopefully no more than one of you, will do on the test next week, or in a week and a half. There'll be somebody who does this exact same problem like this. 1 to 4, 1 over x minus 2 to the 2/3 dx equals, I'm skipping a couple steps, but that's okay. You would have followed, filled those in, I'm sure. Evaluated from 1 to 4. And then you would have had 3 times 2 to the 1/3 minus 3 times 1 to the 1/3. And you would have had 3 times, that was a negative. Lost a negative somewhere. Negative 1, there it is. I got too fast. Negative 1. 3 times the cube root of 2 plus 3. It's really sloppy. It's a tiny cube root. Same answer. If this problem was worth 10 points on the exam, I think I might give you 3. Even though you got the correct answer. Why? 3 out of 10 is all you're getting.
We just skip all the steps and you grade by the step.
Yeah, well, yeah, you're skipping the steps and I'm grading by the steps, which is true.
You didn't check.
You
if
didn't
there's
check.
a Undefined.
Right where it was undefined. It's just as likely to diverge as it is to converge. You can't tell unless you check the limits where it's undefined. So this particular one, because it converged, you would have gotten lucky and got the right answer. But if it diverged, you would have had that answer and the answer should have been divergent. There's at least one of them on the lab, that Chad and I were talking about at the break, that he did the shortcut before he had learned it. He was trying to work ahead. He didn't learn the hard way. But he got an answer, and how come my answer key says it diverges? For this very reason. If this limit goes to infinity, that changes the whole answer. You have to check those limits. Guess what you got to put on the exam? Probably the one that diverges. But you don't know for sure. You can't trust me. How are you feeling? A little bit messy. Yes, sir.
Are we gonna have any where the limit is undefined, but it's not readily seeable in the problem?
I guess I don't know what you mean by that. Like the limit's hard to calculate?
Yeah.
So I guess the definition of hard to calculate and readily seeable isn't totally obvious. So there are some limits that you might have to use some of your techniques from Calc 1 to do, where maybe you want to use L'Hopital's rule, or maybe you would need to, reduce by highest powers of x. There might be a couple things that you might not totally remember, but you probably, as you work through the lab, you'll jog your memory on those. So there's not going to be any limits that are, impossible to calculate, but they might require some stuff you learned in Calc 1. I can't say off the top of my head because I don't have them in front of me right here. Do I have one of those in here? I think the one I skipped might have been one of those. Was it? Let's see. Oh, it was. Let's go back to example 4 then, because that's one that maybe falls into that category. Did I do the other examples on here already? I did, correct? Yes. Okay, let's go back into example 4 on page 58. And I think it might be one of those that Zach's asking about. You guys want to get started on your own with that one, or you want me to walk you through it? Example 4 on page 58. Giving you options. Anybody have a strong opinion one way or the other? Okay, I'm letting you guys get started and then I will walk through it. I'm not going to be walking you through it on the exam anyhow, so you might as well try. So here's the question. At least this one's one that we recognize as an improper integral. And I like it because it's a review problem too. Why is it a review problem? Integration by parts. So, work on that for a few minutes, maybe 5 or so. See how far you get. You're going to need to rewrite it because it's improper, but then you also need to use your integration by parts. That'll be fun. And then we're going to finally get to the question about the limit that Zach was asking about an hour ago, it feels like. So the first thing I did was rewrite it with the limit here. B is approaching infinity. Right? And then I recognize that this needs integration by parts. So I just brought the indefinite integral over here without the bounds, and I'm just working on the integration here first, and I'm gonna bring it back over here in a minute. So the integral without the bounds, I chose my u, found my du, my v and my dv. We're doing all of our integration by parts. So this is my u times dv, excuse me, u times v, minus integral of v times du. I think I kept track of my signs. And then I had to integrate this guy, again, the integral of that ends up being plus e to the negative x. So this is just the integration by parts. So let me pause there. Questions on this portion up here, the integration part? Lots of negatives, lots of places. You know, lots of people nodding, which is good. Okay, so if that's the integration, if I'm over here, I have the limit as b approaches infinity of negative e to the negative x times 1 minus x plus e to the negative x. I can drop my plus c now, evaluated from 0 to b. Yes?
Been all right to have multiplied that out, and then doing limit of b goes to infinity.
Oh, that's fine. Distribute this through?
Yeah.
You'll get the same answer either way. Everyone see what he's asking? He distributed here. Whether you distribute now or later or you don't, it'll end up being the same answer. So now I'm going to plug the b's and the zeros in there. Limit as b approaches infinity of negative e to the negative b times 1 minus b plus e to the negative b minus, got too many things going on here. Now I'm plugging in my zeros. Negative e to the 0 times 1 minus 0 plus e to the 0. Have to plug your zeros in this time because they might make a difference because e to the 0 is not 0. Still okay? Let's clean up a little bit here. What's e to the 0?
1.
Yeah, so this is negative 1 times 1 plus 1. This term over here. So it actually is all 0. We had to check that. That one's gone. And now we're here. Just this part now, right? And b is approaching infinity. I personally can't think with negative exponents as easily as I can think with fractions when it comes to limits. So I like to rewrite my negative exponents as fractions to help me see what the limits are doing. So I'm going to rewrite this problem this way. If you can think with negative exponents, good for you, but it's easier for me not to. So this is negative 1 minus b over e to the b. This is on top, it's got moved to the bottom as positive b. Plus 1 over e to the b. So I just rewrote my e to the negative b's as 1 over e to the b's. Those guys are all 0, so I dropped them. So the first one I want to ask you about is what happens to this term? As b approaches infinity, what happens to this term right here?
Becomes 0.
Becomes 0, right? Because you get 1 over infinity, 1 over anything infinitely large. We talked about that one earlier. That part's 0. This is the part that throws people for a loop. Because if I plug infinity in here, if I think about the limit, I end up with a negative infinity on the top, and infinity on the bottom, and infinity over infinity is not necessarily equal to 1. Infinity over infinity could be square root of 2 for all we know. All depends on what's going on. That's what's called an indeterminate form. Everyone agree that it's approaching infinity over infinity right now, and so that's where we're stuck. So at this point, this is where you want to use your friend L'Hopital. L'Hopital's rule you learned back in Calc 1. whenever you have infinity over infinity, you can take the derivative of the top and bottom separately and then take that limit. So I'm gonna bring just that part over here so we can see it. So we have the limit as b approaches infinity of, I'm going to distribute this negative inside here so I don't lose it. You guys okay with that? So it'll be negative 1 plus b. Just so I don't lose it, there's too many negatives. What we say is, we put a little h there, says we're gonna use L'Hopital's rule. Because right now it's infinity over infinity, right? Oh bad, we don't know what infinity over infinity is, it's just unknown. But L'Hopital's rule says I can take the limit of the derivatives. So I'm taking the derivatives with respect to b, that's my variable here. So what's the derivative of the top? Derivative of b is 1. Derivative of the bottom, e to the b. Now can you take the limit? Yeah, now it goes to 0. Infinity over infinity turned out to be 0 in this case. Equals 0. What does that mean when an integral equals 0? What's it mean in terms of the graph? What should the graph look like if it adds up to 0?
It's like goes like the portion 0 by something over 0.
But the integral approaches 0. The integral is the area under the curve. What were you going to say, Sebastian?
Would part of it be, like it would match itself almost as if it was rotated over the axis?
I like what he said. He said it would match itself like it's rotated over the axis. So however much area is above the x-axis, you must have the same amount of area below the x-axis for those to add up to 0. I don't know what the graph of that one looks like, but imagine like a sine function. Right, the integral from here to here would be 0, because this area and this area are exactly the same. So this, I doubt it's going to be symmetric in terms of its shape, but in terms of its area, apparently the part that's above there and below there is equivalent. We'll have to graph it later and see. So that's the answer to your question, Zach. You might end up with something like this that requires L'Hopital's rule. Infinity over infinity. That's probably the worst case of what you'd end up with.
Okay.
That was a long, messy one. That's everything we got in this section, though. We're done early. How often does that happen? So I'm gonna hang around in here for the next 15 minutes or so if you want to start working on the lab. If your brain is dead, I'm fine with that too. I will then be in